All right, so I've got that same chemical reaction model over here. I've cleaned it up a little bit. I have my red-blue molecule bonded together, and I have my green-purple molecule bonded together. Those are my reactants. As they collide in this kind of direction into each other, they collide like this. As that happens, we get to this transitional state where my bonds here and here start breaking, and my bonds here and here start forming. So we hit that transition state. We're in the right orientation. We're taking up energy to break bonds, and we're using energy to make new bonds. And so we're going to talk a little bit more about this reaction in terms of energy. And to do that, what I want you to do is think back years ago when you first learned about potential energy. So we're going to shift gears and then come back to our reaction equation. So I want you to think about when you first learned about potential energy. Very likely you were given the diagram or model idea that you have a slide like this. This is like a playground slide. When you're at the top, you're told you have a lot of potential energy. And then when you go down the slide, as you get to the bottom, your potential energy is being converted into kinetic energy. And at the bottom, you have a low potential energy. So here, we're going to have something similar that we're thinking about, except instead of thinking about gravitational potential energy, which is what this example uses, we're going to think about chemical potential energy. And every molecule contains chemical potential energy, and how much chemical potential energy they have is determined by how stable that molecule is. The more stable a molecule is, the less potential energy it has. And the reason for that is kind of similar to the example with the slide, actually. So when we think about our slide example, the higher we are, the more potential energy we have, because the farther we have to possibly fall, right? So in our chemical examples, the more stable a molecule is, the less crazy of a reaction we're going to get in response. So we can kind of think of our potential energy as like the potential to be an explosive reaction. So the less stable, if we have like a really, really unstable molecule that's just kind of squished together and doesn't really fit together nicely, that's going to have a really high potential energy. Think about when we looked at that example of the whoosh bottle. Ethanol is really flammable. It has a lot of potential to react. So ethanol is an example of a molecule with a really high potential energy. Whereas the products that that combustion reaction makes are carbon dioxide and water, which have really low potential energy because they're really stable molecules. So if we were to draw a diagram, actually I'll leave this up. If we were to draw a diagram of a reaction, what we want to think about is the amount of potential energy that the reaction has as the reaction is taking place. So I'm going to draw a diagram, and on my vertical axis, I'm going to label that with potential energy, which I'm going to abbreviate as PE. So my potential energy, and the higher I am on this graph, just like the higher I am on this slide, the more potential energy I have. And then across my horizontal axis, this is just going to be time. This is as the reaction goes on. Just like this slide, my horizontal axis would be time, because this is the start of me being on the slide and this is the end of me being on the slide. So with my reaction, what I can draw is I can draw the amount of energy that my reactants have. Whoosh bottle example, because I'm thinking of it. So my whoosh bottle example, my ethanol has a really high potential energy. It's up high on this diagram. And then my carbon dioxide and water that I make, those are really stable. They're going to be pretty low on this diagram because they have pretty low potential energy. But we know that we're not just going to get from, this is, let's call it ethanol and O2 now, because that's what those reactants are in that reaction. we're not just going to go straight from ethanol and O2 magically turning into carbon dioxide and water. We have to hit this transition state first. And that takes energy because it takes energy to break the bonds in ethanol. So because it takes energy, we actually have to get to our transition state first. And so we're going to hit this peak. So we have to go up in energy first to get to a transition state. And then my energy is going to fall to my products in this case. So in this case, I have a really high energy reactant, my ethanol, and I have really low energy products. And it's going to take me energy to get up to that transition state. What I have here is called a potential energy diagram. And whatever is on the left of my potential energy diagram is always going to be my reactants because I'm looking at time as my horizontal axis. So reactants are always going to be on the left and products are always going to be on the right. And it's always going to take some amount of energy to get up to my transition state because I always have to break the bonds of my reaction first, and breaking bonds takes energy. So I'm going to label a couple more things in here. So we said that the amount of energy required to get to my transition state, we labeled that in our last video. We said that was called activation energy. So I'm going to label that here. So this amount of energy is equal to my activation energy. And then I can think about too, well, where did this energy go? So in the gravitational example, it turns into kinetic energy. We're moving down the slide. But where does all this energy go when we're thinking about my chemical reaction? Well, in the whoosh example, it's lost as heat. We've seen that. We saw that example. We saw the ethanol burn. We got this crazy burning reaction, fire formed. We got light energy and we got heat energy out. So in this reaction, we're getting energy out of our reaction. It's leaving this system. And if I take whatever this number is and I subtract away my ending number, that's going to be the total amount of energy that is released by this reaction. So I'm going to draw another arrow here. From here to here, this is going to be my change in energy. And I'm specifically referring here to energy that is lost as heat. And so this is actually abbreviated with a delta H. That H doesn't actually stand for heat. It stands for enthalpy because the change in energy that we are looking at here is enthalpy. All right, so again, I have a slightly cleaned up version of the picture that we were looking at, and we're going to label it again together for practice. So I want to look at this energy diagram. On this side, I have potential energy. Down here, I have time, and I want to go in and I want to label where my activation energy is. I want to find the amount of energy that's released by this reaction. And then I want to see where is the amount of energy, and I'll change color for this. How much energy do my reactants have? How much chemical potential energy do my products have? And how much chemical potential energy does my transition, my in-between state have? So I want to find all of these on this graph. So let's start with my reactants and my products. So the amount of energy that my reactants have is going to be whatever this number is right here. So this is the energy of my reactants. And then at the end of the diagram is always going to be the energy of my products. So whatever this value is right here, this number would be the amount of energy that my products have. And to figure out the amount of energy altogether that is released, I'm not just going to do products minus reactants because that would get me all the way to up here and doesn't take into account that some of that energy of this whole reaction gets used up, breaking the bonds in my reactants to get to my transition state. So up here, I have that in-between state. I'm not ever going to ask you to draw a transition state for me. I just want you to know that there is something that has to happen in between where bonds are broken and new bonds are formed. And we said that the amount of energy that it takes to get from reactant to products, that's going to be my activation energy. So whatever this number is here, minus this number here, that difference in this area here, that difference is going to be the amount of energy that is used out by this reaction to create the transition state. And then after I get to my transition state, I'm going to release the rest of that energy as heat. So this is going to be my delta H, which is going to be equal to whatever this number is minus this number. So let's throw some actual numbers on here. Let's look at some calculations. Let's look at totally fake, made up numbers. These are not representative of a real equation, but let's say that this is 10 kilojoules. Let's say that this is 100 kilojoules. And let's say that this is 90 kilojoules. And kilojoules is just a unit of measurement for energy. So if I want to find my delta H, I can actually calculate that from my graph. I can say delta H is equal to the energy of my products. So we can think of this as like final minus initial, like when we looked at delta T, change in temperature. This is change in enthalpy. So this is going to be equal to the enthalpy of my products, my final, minus the enthalpy of my reactants, my starting. So the enthalpy of my products in this example is 10 kilojoules, minus the enthalpy of my reactants was 90 kilojoules. Since my reactants had more energy than my products, I'm getting a negative number here. And I'm going to make a note of that a negative delta H means energy released as heat. And this happened because the amount of energy in my products was less than the amount of energy of my reactants. So when the amount of energy that my products have is lower than the amount of energy I started with my reactants, that means that energy is being lost to the system. It's leaving as heat, just like in my fire whoosh bottle example. This is called an exothermic reaction. And let's look at that word a little bit. We have exo. This prefix means out. Thermic, we can think of like if you're wearing a thermal or if you have a thermos, this means heat. So exothermic means that heat is going out. So we have an exothermic reaction whenever the energy of the products is less than the energy of the reactants. That is an exothermic reaction. It means that heat is released. If you touch an exothermic reaction, it is hot. If I look at the whoosh bottle example, it's releasing fire. That's very exothermic. That is a lot of heat coming off. So exothermic reactions release heat out. They have a negative enthalpy, and the energy of their products is less than the energy of their reactants. And they look like this on a graph. But not all reactions release heat. So I have another diagram on the right, and I'm going to kind of just draw a separator here. So this was our exothermic reaction over on this side, and now I'm going to draw another type of reaction on the right. So we said that the reason that my reactants on the exothermic reaction, the reason my reactants had a pretty high potential energy was because we were starting with a relatively unstable molecule compared to our products. So my reactants were less stable. That means they had more potential to react. So they had a higher potential energy. But sometimes I start with a more stable reactant that's down here. So I start with a reactant that's really stable. So its energy is going to be down here. And then I end up with something that's less stable. I'm like a mad scientist. I'm making something explosive. I'm making an unstable product here as compared to my reactant. So here in this situation, my reactants were more stable, which means that they had lower energy. They had less potential. They're really stable. They don't want to react. They're happy the way that they are. My products have pretty high potential energy. They are less stable, ready to react. Lots of potential there. So to get to my transition state, to get all the way up to my products, I need to break really stable bonds. I need to break the bonds of a really stable, happy, low energy molecule. That's going to take a ton of energy. I don't like the curve on that. So my transition state is going to be up really high, and that's probably too high. Let me try it from this side. That's a nice curve. Okay, there we go. So my transition state is going to be up here because I still need to break those bonds in my reactant, and it takes a lot of energy to break the bonds of a really stable molecule, which means my activation energy is going to be huge. It's going to be this whole difference here. So the amount of energy that it takes to break the bonds to get to my transition state is really high. This has a much bigger activation energy. It takes a lot more energy to break the bonds of a low energy stable reactant. And then here, my delta H is going to be a net value. So then from here to here, I'm going to release energy back out, some of it. But most of the energy involved in this reaction went into that activation energy. And then here is going to be my delta H. So again, it's still going to be the energy of my products. So remember, delta H equals H products minus H reactants. So it's still going to be my products minus my reactants, but now we're going to end up with a positive number. If I had these same values, if this was at like, let's call this, now this would be my 90, this would be my 100 up where the transition state is, and then this is my 10. My products minus my reactants, my delta H is going to give me 90 minus 10. I'm going to get a positive 80. I don't need that plus, but just to kind of really make it clear. So this is what we call an endothermic reaction. Endo has the opposite prefix. So here we said exothermic meant out. Exo is out. Therm is heat. Endo means in. So this is heat in. If you touch an endothermic reaction, it's cold to the touch. And that's because instead of this energy being released as heat, this energy is being absorbed and used up to get to this transition state. And then a tiny bit comes back out, but our net is all of this. So we've taken in way more energy than we've let out. So we are going to have energy going into the system. It's taking heat in. My challenge for you guys, take a water bottle, pour some vinegar in it, pour a little baking soda in it, and then hold the water bottle. The reaction between vinegar and baking soda making carbon dioxide, that's an endothermic reaction. It will feel cold to the touch. So you will feel that reaction pulling in heat from your hand and using that heat energy to create its transition state in order to make carbon dioxide. So again, just to recap, my exothermic reaction is going to look like this on the left, where we have our reactants up at the top, our products down at the bottom. And then my endothermic reaction is going to look like the one on the right with the reactants on the bottom and the products up on top. Either way, we've got to get to a transition state. And we're going to get a negative enthalpy for an exothermic reaction and a positive enthalpy for an endothermic reaction.